Hey Sutir, glad you could join me today. I've been going through that interface flux assignment, and honestly, there is so much packed into it. Though it would be cool to break it down together.
Hey, wait, yeah, same here. It's a lot of technical detail, but once you get into it, the concepts actually fit together pretty neatly. Let's start with the basics and one of the fundamentals before diving into the complex parts.
Good idea. So to start, we are essentially looking at interface flux in momentum transfer, right? This is all about how momentum moves between fluid layers, especially when it interacts with a solid surface like a flat plate.
Exactly, and that's where the drag force comes into picture. When a fluid flows over a flat plate, it creates a shear stress on the surface due to viscosity. The friction between the fluid layers and the plate generates a resistance force, we call it the drag force.
Right. And I like how the assignment actually walks us through deriving the generalized equation for drag forces. It takes into account the velocity profile, the no-slip boundary condition, and how the friction factor plays a role.
Yeah, speaking on the friction factor, it represents the resistance to flow due to friction. It depends on the surface roughness and the fluid's Reynolds number. We will get into detailed physical interpretation of it later on.
For sure. And I also noticed some real-world applications, like the power consumption of a sports car in different wind conditions. That part was really pretty interesting. How the drag force changes when the wind direction varies.
Definitely, that example really shows how the theory applies to the practical problems. It's not just the equation, it's about optimizing performance and understanding how the friction impact the energy usage.
Exactly. So let's kick things off by breaking down the drag force derivation first. Then we can move on to the friction factor interpretation and finally tackle the power calculation problems.
Sounds like a plan. Let's get started. Now we will understand what is interface flux.
Alright, Sudhir, let's get straight to the point. What is interface flux?
Interface flux is the rate at which a quantity like momentum, heat, or mass is transferred across the interface between two phases. For example, from a solid to a fluid or from a gas to a liquid.
And this transfers happen because of difference or gradients, like velocity gradient in momentum transfer, temperature gradient in heat transfer, and concentration gradient in mass transfer.
Exactly. There are two main contributors to this transfer. Molecular flux, which is the due to the diffusion or conduction, slow microscopic movement. Convective flux, which comes from the bulk movement of the fluid like wind carrying heat or particles.
So the total flux is just sum of molecular and convective flux. It's kind of like saying what is moving because of random motion plus what is moving because of fluid in fluid.
Exactly. That's the core of the interface flux, microscopic and macroscopic movement working together to move stuff across boundaries.
So Suthir, let's get straight into it. Interface flux sound fancy, but at its core, it's all about how momentum, heat, mass transfer between phases, right?
Yeah, exactly. It's basically how something, whether it's force, energy, or particles, move across a boundary. We see this everywhere. The air flowing over a car to heat moving through the wall. Now, today, we will discuss about a problem that will be shown on the screen.
Right. And in our case, we start with momentum transfer, particularly in context of a flat plate in a fluid stream. Imagine you have a metal plate suspended in a river and the water is flowing past it. The water has certain velocity as it approaches the plate.
Yeah, and the surface of the plate, due to no slip boundary condition, the velocity of the fluid is actually zero. So now, as we move away from the plate into the fluid, the velocity gradually increases until it matches the free stream velocity of the fluid.
Suthir, can you please tell me what is no slip boundary condition?
A fluid in contact with a solid surface sticks to it, meaning the fluid's velocity at the wall at the surface is equal to the velocity of the surface wall. In this case, we have this no slip boundary condition.
That transition zone, where the velocity is changing from zero at the surface from the free stream velocity, it is called the boundary layer. This is where all the momentum transfer happens.
Exactly, and the thicker the boundary layer, the more it affects the overall flow. The boundary layer is important because the drag force experienced by the plate comes from the shear stress inside it.
So let's break that down. Drag force is basically the force that exerted by the fluid on the plate in the direction of the flow. It arises due to friction between the fluid and the flat plate surface.
And the key quantity that determines the drag force is the shear stress of the plate surface. Shear stress is essentially the force per unit area due to fluid viscosity.
Right. and the viscosity is just a measure of how the resistance the fluid is to flow. For example, honey has high viscosity and air has low viscosity.
Exactly. Now we can express a drag force mathematically. We integrate the shear stress over the entire surface of the plate to get total force.
Yes, that gives us a key formula. Fd equals to integral tau w into dA, where Fd is the drag force, tau w is the shear stress, and dA is the interface surface area.
So now we will derive generalized equation for drag force in interface flux and momentum transfer. In our case, we have a flat plate of length L and width W. We have a flow stream of velocity V infinity and direction coordinates are such as we will consider S direction as flow of stream and Y direction perpendicular to the flat plate. Now generalized equation for drag force, we can equate Fd equals to integral tau W into dx into dz, where our dx varies from 0 to w, w is width, and dz varies from 0 to l is our length. In our case, our tau w is equal to interface flux pi by x. Tau w is our shear stress. Ba- Basically, interface flux is equals to molecular flux at interface plus convective flux at interface, which can be denoted by pi by x equals to tau yx plus rho vx into vy. In our case, we have no slip boundary condition due to which the relative velocity is zero and our convective flux will be zero. So hence we can equate pi by x equals to tau yx, which is interface flux equals to molecular flux in our case. Now we will equate tau w equals to pi yx. Now substituting the value of tau shear stress in above equation, which is equals to mu dvx by dy, which equals pi yx. We also have tau w equals to half rho v infinite square into f. It is finding equation where rho is density and f is frictional factor. Now we will substitute the finding equation in our generalized drag force equation. So as we know that density is constant and velocity of flow stream is also constant, so we can take it out from the integral. Here we have the generalized formula where f, now we have the generalized FD equation as half rho v infinite square into f into WL, where f is average friction factor and W into L is characteristic area and half rho v infinite square is characteristic kinetic energy. Now we
And to
can
make sense, we introduce something called the friction factor. It's a dimensionless number that helps us quantify the drag resistance.
Yes, and it is related to Reynolds number, which tells us whether the flow is laminar or turbulent. For example, the flow which is smooth, we can consider it as a laminar flow, and the flow which is chaotic is mostly turbulent flow.
And higher the turbulence means higher the friction factor, meaning more resistance. Now, this concept isn't just theoretical, it's super important in real world engineering.
Yeah. For example, in aerodynamics, friction factor affects how much energy a car or an aeroplane needs to overcome the air resistance.
Exactly, speaking of which, let's apply this to a practical example calculating the power consumption in a sports car. But before that, we will see how we will derive the friction factor on the screen.
now we got our generalized Dykforth equation, which is equals to ACH into KCH into average frictional factor. Now KCH equals to half rho VCH square. Now we will derive our average frictional factor. Average frictional factor equals integral 0 to W integral 0 to L f dx into dz divided by integral 0 to W integral 0 to L into dx into dz. Basically, dx varies from 0 to W and dz vary from 0 to L. F is a frictional factor. Now here we can clearly see that denominator is nothing but area, surface area of flat plate, which we can take out and write it as 1 upon WL. This is our average frictional factor formula.
So now we'll understand how to calculate power consumption using drag force. Now given the problem, a sports car usually have a friction factor of 0.24. So friction factor F is 0.24. The car has an equivalent width of W equals to 2 meter and length L equals to 1.5 meter. You can read the given question. Now we have to find out the power consumed by the car when it is going at a speed of 100 km per hour with no wind blowing. So V is given as part A. V is given as 100 km per hour, assuming no wind blowing. So calculate V equals to 27.78 meter per second. Also we have rho as 1.2 kg per meter cube at 20 degrees centigrade. And assumption is air is at 20 degrees centigrade is given in the question. That air is at 20 degrees centigrade. Okay. So let's continue with the problem. So we know that FD equals to ACH half rho VCH square into average friction factor, that is given in the question 0.24. This we have derived in the previous slides. Now we also know power P or W equals to FD into VCH. So for question part A, we need to find out what is FD. So FD is equals to half into 1.2 into 27.78 the square into 2 into 1.5 into 0.24. We get it as 333.4 Newton. Now we'll have the power consumption, that is equals to 333.4 Newton into 27.78, that is equals to 9262 watt. This is for no wind blowing condition. No wind blowing condition. So from drag force FD, we can calculate the power consumption for an engine. Okay, now we have the part B. What does part B says? Part B says, repeat part A if the wind blows at a velocity of 30 km per hour opposite to direction of the car. So the wind is blowing at 30 km per hour. So what will the characteristic velocity? VCH equals to 100 plus 30 km per hour. Okay, so we have the total velocity as 130 km per hour, that is equals to 36.11 meter per second. We have to convert everything in meter per second as the units needs to be same. So now I have to calculate FD. FD is equals to 36.11 cos square. It is half, and we have rho 1.2 into VCH cos square into 2 into 1.5. 1.5 to 1.5. What is this? 1.5. 2 into 1.5. That is area, ACH, into 0.24. That is the friction factor. 563.3 Newton. So power consumption will be 563.3 Newton into 36.11. That is the VCH, that will be given as 20,341 watts. So we can see that if the wind is flowing at the direction opposite to the car, the power consumption for the engine is much higher. Now, if the wind is flowing in the direction of the car, that is a part C, that you can take it as homework. What will be the power consumption? You will see that the power consumption for this case will be much less than the power consumption for the case B. Thank you. That's it for the power consumption.
So the problem is solved. Now let's break it down. We have got a sports car. Friction factor is 0.24. Width is 2 meter. Length is 1.5 meter. And it's moving at 100 km per hour.
Right. The key idea is this: the car experiences drag from the air, which is resisting its motion. To keep moving, the car's engine has to do work against the drag, and that's where the power consumption comes into picture.
We calculate the drag force using the friction factor and the velocity. Then power is simplified. P equals to F into V. That means how much force the air is pushing back multiplied by how fast the car is moving.
And we always express velocity in meter per second, so 100 km per hour becomes 27.78 meter per second.
Once we get the drag force, we plugged it in and boom. We know how much power the engine needs just to overcome the air resistance.
And here's where it gets interesting. If wind blows against the car at say 30 km per hour, the car now feels like it's going faster relative to the air, 130 km per hour. So the power consumption increases.
But if wind goes with the car, say same 30 km per hour in the same direction, then the air relative to the car is only 70 km per hour. So the drag is less and the power consumption drops.
So wind isn't just an annoyance, it literally changes how much fuel your engine needs to burn.
That's why aerodynamics matters so much in vehicle design. Less drags means less power and more efficiency.